Everybody see all right? Okay, this is in the lecture outline, chapter 4, chemical stoichiometry. That is the mathematics or the application of mathematics to chemical concepts. Yes. We will continue to follow the Dalton's law of atomic theory, or not the Dalton's law, but Dalton's atomic theory, and that we will begin with some of the basic concepts and build up to the more complex concepts. Now, the beginning effort, and if you have your outline, hopefully you can keep this, and I will be following this to the letter. And so you will know where I am as we go through the material. So we begin with the concepts of the mass and the mole. Now, as long as we stay on the surface of the earth and in this reference frame, mass and weight are going to be equivalent. So we're going to, if I use the term mass, it's going to be the same thing as if we were using the term weight. Now, in the concept of mass, the idea is to apply to formula weights and atomic weights. Now, one of the things I want you to note real fast here is substance. The term applies to both elements and molecules. And in that, they're both homogeneous, in that they have their own specific properties and so forth. So I'm going to give you a definition that's going to say something in terms of substances. Well, in your mind, keep elements and molecules both apply to the terminology. Okay. Now, one of the first issues most of you already know, and so I'm going to work a couple of problems on this, and we will move on into the mole concept. So, formula weight. Now we have formula weights of elements, and we have formula weights of molecules. The formula weight of an element, just to add a note to your notes, typically is, of course, the atomic weight. Now, in working problems, I found it easier and more expedient to round to the nearest whole number on these formula weights. Oxygen, for example, has 15.9994. 9994, if I can get the right digits, 4 atomic mass units. So if I'm working a problem or something, I'm not going to go to that extent. And if you have a need to go to significant numbers after the decimal place, look at your answer choices, or if you want to carry it out that far, it's your choice. But as I go through these lectures, I'm just going to, if I have to use weight of oxygen, 16 atomic mass units will be used, and so forth. Sulfur, 32, hydrogen, 1, and so forth. So I'm not going to go into the greater number of digits on the south end, if I call it, of atomic weights. Now, sometimes it may be necessary to carry digits out, but in generalizations that we'll be making, that's as far as we're going to go. Now, we talk about formula weights of molecules. As you are aware, and heard many times, is molecular weight. And up to this point, we haven't emphasized the gram issue as much. So you've heard both terminologies of atomic mass units when we add everything up. From here on, we're going to be using grams per mole. So from here on, it'll be grams per mole, and that's gram molecular weight. Just to establish some ground rules in terms of terminology that we're going to be used. Now, a couple of problems that may be needed. H2O, how do we get a formula weight? Well, it's obvious, it's 2 hydrogens and 1 oxygen, and in that I will multiply 1 plus 1 times 16, and let me get that, and it'll be grams per mole, and of course that will be 18 grams per mole. That is 1 mole weight of H2O equals 18 grams. So we'll get to that in more detail and its importance here in a moment. Sometimes formulas, as you well know, come with some clutter to them. And so let's take calcium phosphate, for example, like this, subscript and 2, just to emphasize the nature of symbology in calculating formula weight. So in calculating a molecular weight of calcium phosphate, we have 3 calciums. 2 applies to everything in the parentheses. That'll be 2 phosphorus plus 8 oxygens. And then we substitute the formula 3 times 40 atomic weights plus, I forgot what phosphorus is, 30.9 or 31. And 8 times 16, and we call that grams per mole. So that's 120 plus 62, 128 grams per mole. And so 8, 9, 10, 2, 3, 11, 310 grams per mole. So if there's any difficulty in following what I did, please let me know, and I'll point it out. If something doesn't make sense, if I put the wrong subscript, ask me. One other that I think you need to put in your notes is, say, a hydrate, copper sulfate, and you already seen this in our lab work, 5H2O. It is, the dot in there does not mean multiply, it means add however many waters to the formula weight. So we're looking at 1 copper plus 1 sulfur plus 4 oxygens plus, which would be the dot, 5 H2Os. Now, this is so simple to calculate. 16 and 2 is 18, so why don't we just stuff it in that context. And let me see what copper is. You will all have, of course, the periodic table available to you. Copper is 64. We'll go 1 times 64 plus 1 times 32 plus 4 times 16 plus 5 times 18. Everything works out to grams per mole, as you would expect. So that would be 64 plus 32, 46, 48. Oh, sorry. 6 and 4 is 24. 64, not 48. 5 and 8 is 40, 90. There we go. And grams per mole. And so, this is 4 and 4 is 8, 9, 10. 9, 10, 16, 17, 18, 19, 21, 2, 3, 4, 25, 250 grams per mole. So there are 3 model examples that I think you're well aware of for the most part, but I think it is important that we just kind of make a comment about them so that we're all working in the same context and terminology. very, very important concept here because it's applied from this point all the way through the textbook. I will use this in a format that you may or may not have heard of. You will hear me many, many times as you work chemistry problems say, convert to moles, solve the problem. If they want something else, convert it back later. You'll hear that over and over and over. Work a chemistry problem in terms of moles. It simplifies it manyfold. 1 mole is a weight measurement. And think of it as a mass or weight measurement. And we could go into the philosophy of the terminology, but I'm not going to do that. It's a waste of time. I've seen professors do that, and it just confuses people. Focus on what the term means in chemistry. A mole is the mass or weight of substance that contains 1 Avogadro's number of particles. That mass of substance that contains 1 Avogadro's number of particles is always a formula weight. That is 1 mole weight always equals 1 formula weight, expressed as grams. And of course, it represents grams per mole. So 1 mole equals so many grams. If we consider it, I wanted to know substance. It is the mass of a substance. And in the beginning of this, I asked you to remember that a substance applies to the elements as well as the molecules. So we're saying a mole of a formula weight of element, or a mole of formula weight of molecules. So when we talk about, say, 1 mole weight of oxygen, we can simply say that's 16 grams. Or 1 mole weight of hydrogen is equal to 1 gram. Gram mole weight, however you wish to use it. However, if you apply this to, let's make this heading, molecules, look at the similarity as how I write this. 1 mole weight of water equals 1 formula weight, which is 18 grams. 16 plus 2 is 18. Or 1 mole weight of sodium chloride is 1 formula weight, which is 23 plus 32. What is that, 23 and 32? I don't know. I think it's 58. Wait a minute, that's why I'm throwing me. Sodium is 23 and 35. 23, 35, 7, 8, 58. Yeah, that's what I'm saying. 58 grams. Okay, so anytime we're talking about a formula and you need the 1 mole of it, add up the elements and you get the formula weight. Now the mix in this is, and you get subscripts and so forth and so on. Now let's take a 1 mole of lead chloride. Okay, plus 2, 2 unique couple of carbons. So this is 1 mole weight of lead chloride. Okay, so how many moles of lead chloride are you looking at? You're looking at one, right there, that, you know, like that. But how many moles of chlorine are you looking at? 2. The subscripts are multiples. Now, you see how I'm making that judgment right here? 1 mole of formula. Now, if you throw in a subscript, then it multiplies that number of moles. Because you'll have problems. They're going to test, says, how many moles of chloride do you have in this? Well, it's 2. So it is very important that you get comfortable with interpreting subscripts in the formulas just as you would looking at a formula, saying, well, that's 1 formula weight. Well, how many, and which is 1 mole? Well, then how many moles of chloride do you have? Okay, well, that's 2, because it's part of the whole molecule. 1 mole of copper, 2 chloride. We can go there. Same thing. We have 1 mole of copper and 2 moles of chloride. So those subscripts. Oh, I got one. It's kind of an interesting 1 mole of, let's see, calcium phosphate. Let's go back to the calcium phosphate. 3 and 2. Excuse me. 3 and 2. Okay, so the problem on the test, they ask you, well, how many moles of phosphorus do you have in here? 2, because of this right here. All right, you have 1 mole of calcium phosphate, but if they happen to ask you something like, how many moles of oxygen in this problem? 8. So you have to take into account this subscript applies to everything in the in the parentheses. So we have 3 moles of calcium, 2 moles of phosphorus, 8 moles of oxygen. And of course that gives you your mole weight if you substitute the atomic weights in there. Some of you are very good at this, but if you're not familiar with it, please learn it reflexively. So we'll start with the idea of grams going to mole. Given in grams and are asked how many moles, the approach is divide by formula weight. That's the simplicity of it. If you're given N or M moles of a substance and they want how many grams, is simply multiply by formula weight. Now these should be learned reflexively and without question be able to handle it, because it will be the base step in working other steps in many chemical problems. Okay, you're given 285.67 grams of H2O2, hydrogen peroxide. Calculate number of moles. Well, you need the formula weight of H2O2 and divide it into the 285.67. So the formula weight of H2O2 is, of course, 2 hydrogens, 2 oxygens, 2 times 1 plus 2 times 16, and that's grams, formula weight, and 2 plus 32 grams, just to string it out for academic reasons, 34 grams per mole, if you want to emphasize that issue right there. Now the question is converting to moles. The way you convert grams to moles, you should think in this mindset. How many formula weights are there in the given? How many formula weights are there in the given? That is, how many 34s are there in 285.67? So that's the essence of what mole calculation is. Moles is 285.67 divided by, well, I'm going to go ahead and put the units in so you can see that, 34 grams per mole. Make that a little neater. 34 grams per. You'll see as a calculator answer what I pulled off of here. What do you use to round this off? You use the data point, not the mole weight. Use the data point. Here, 1, 2, 3, 4, 5 sig figs. And I just made up the number. But as you read your problem, any kind of conversion factors or any kind of formula weights that you add up to make the conversion with is not part of the sig figs. It's the data point. Why? Because it relates to the instrument that you're using to generate that data point. So 1, 2, 3, 4, 5, so that'd be 8.4021 grams. I don't know, it's just an outcome of making up a problem for you. Given 0.002835 moles of O2 gas. Calculate mass in grams. Okay? Calculate your mass in grams. Well, multiply by formula weight. So we have mass O2 gas, not grams, gas, is equal to 0.002835 mole O2. This unit consists of moles O2 gas. That entire part is your unit. So you want to keep that in correction, and my apologies. Anyway, back here is this one. See if I can improve some. Okay, times formula weight. Well, you're working with O2, not just oxygen, so it'd be 2 times 16 to 32. So it is 32 grams over moles O2 gas. See how I put the terminology out here and the symbology as well as grams and so forth, because you want the number to be identified with whatever you're trying to solve in the problem. So we have moles of O2 gas, moles of O2 gas, grams of O2 gas would be in here, and of course, do we have the correct number of significant figures in here? Well, here's your data point right here. And from left to right, 1, 2, 3, 4 significant figures. From left to right, 1, 2, 3, 4, and I'd say yes, we do. Everybody okay on that? Go back and review sig figs if you need to. The little video is very good on bringing you up to speed on that topic. Formula stoichiometry, as you see in your outline, consists of 2 topics that you need to master here. One of them is percent composition. Percent elemental composition. Given a formula, what is the percent of each element? Let me finish this and I'll be right with you, okay? Percent of each element in the composition, and then we need to learn how determining empirical and molecular formulas. Okay, let's do some elemental percent composition. Okay, you just have to be given a formula. Well, I like water. I know some of the answers to this one anyway. Okay? If you're just simply given a formula and asked to determine the percent composition, it would simply be the percent by weight. Okay, it'd be a weight-weight ratio, formula weight, and the percent by weight of oxygen. Okay, that would entail part over total. Well, the part represents the total mass, atomic mass, of all the elements of that type in the formula. So we have 2 hydrogens to take into account, divided by the formula weight of the molecule. And in oxygen, it would be 1 oxy divided by the formula weight times 100% in each case. So it's element total over the formula weight times 100. And so that's 2 times 1 over 18, and you can drop the units because it's all going to be percentages anyway, times 100%. And for the oxygen, we have 1 times 16 divided by 18 times 100%. And this runs out about 11% in, wait a minute, 11% weight in hydrogen, and about 89% weight in oxygen. We'll do one more that's a little more involved. How about sulfuric acid, H2SO4? So you have 3 of them. Oh yeah, the sum of your percentages should add up to 100%. This calculation from formula weights, where you're determining percent composition from just given a formula, that will always be percent per hundredweight. So if they get 11%, you're thinking in terms of 100 grams of water, and there's 11 grams is going to be hydrogen. So, but you don't have to have 100 all the time. And we'll see that when we do the empirical formula thing. I'll show you in a few minutes. But anyway, this is what's the percent hydrogen, sulfur, and oxygen here. Well, the percent, the formula weight, and I'll tell you that, is 98 grams per mole. So save us some time. Okay, the percent hydrogen is equal to 2 hydrogens over H2SO4 times 100%. Do it that way. Percent sulfur is 1 sulfur over H2SO4 times 100%. And finally, percent of oxygen is equal to 4 oxys over H2SO4 times 100%. Put that up a little bit so you can see what's going on. Okay, so that's simply 2 times 1 over 98 times 100%. That one is 1 times 32 over 98 times 100%. And 4 times 16 over 98 times 100%. And problems on exams will come to you just as exact as these. This shows you the percentages, and if you add the percent compositions, the sum will certainly be 100% in that context. Empirical formula by definition is the smallest whole number ratio of elements within a smallest whole number ratio of elements in a given compound. There are compounds, for example, ethylene, C2H4, and it's a molecular formula. In that it has the actual number of elements in it. I can put the molecular formula definition down here now. You can simply call it the actual number of elements in a given formula. Molecule, compound, however you want to look at it. Now, if this is the molecular formula, it's easy to see that we can reduce that by dividing by 2, and this will give you the empirical formula, CH2. Now, the empirical formula, listen to this carefully, what I'm about to say. The empirical formula may also be the molecular formula. An example is methane. CH4, methane, is both empirical and molecular formulas. In terms of its definition of what it is in that context. However, CH2 doesn't exist in the context of a freestanding molecule, but it is still defined as the empirical formula. And now, before we leave the background information here, I want you to look at this up here real quick. What did I do to get to the empirical? I divided by 2. So what I'm saying is the relationship between the empirical formula and the molecular formula is what we call a whole number multiple. So this little issue is a whole number multiple, and is expressed in, say, molecular formula equals empirical formula times a whole number multiple. Well, that translates very quickly to formula weight times some multiple. Empirical formula weight, molecular weight. So we say molecular weight right here is equal to some n, which is the whole number multiple, times empirical weight. In problems relating to this concept, you have to be given mole weight, but you will determine empirical weight and then divide empirical weight into mole weight to get that whole number multiple, and then write out, take that number and distribute it through as a subscript through the molecule. I'll show you when we get there. Okay. Okay. Let's work some problems. I think in your outline, the second page, you will find this. Yes? Is that behind the first page there or not? It's very straightforward. If the elements are given in parts per hundredweight, and it says carbon is 20%, hydrogen is 8%, and oxygen is 16%, those are in general parts per hundredweight. And so we're going to go, and what I'm getting here, this is from parts per hundredweight. You will go percent to grams to moles a ratio, I think it is, yeah, and reduce your ratio. So R8. And that gives you the empirical ratio. And with that, then you write your empirical formula. Like that. Problems will come to you very much in this kind of context. Here's a couple of them. I'll try to get all three of them up there, I think. Yeah. Here is an oxide of osmium. I give you the formula weight is a pale yellow solid, 2.9 grams of the compound contains 2.16 grams of osmium. What's its empirical formula? Well, this is not beginning in the percent per hundredweight. You have to first use this data to calculate your percent per hundredweight and then follow the sequence. I'll show you. Now here, this one's already given in percent per hundredweight. 65, 55, and then blah, blah, blah. So you just start there, make a list, and go. Here, you'll do one, say here, and then they'll give you a formula weight, and you go on and find the molecular weight. Those are the three types of problems you'll run into in working these empirical formulas. And again, I'll go make a copy of this when... Okay. An oxide of osmium equals 190.25 grams per mole. Okay? And you are given in this problem an experimental measurement that says sample of the compound is equal to 2.89 grams. And it was determined that the weight of osmium in this compound is 2.16 grams. Now you can use this data to calculate your percent per hundredweight. Part over total times 100. This is how you do it. Now, of course, we need the weight. You simply subtract these two and you'll get the weight of oxy in the formula. Like that. Then the percent per hundredweight is simply calculated in terms of part over total. Here is the total, and these are the parts. Of course, that's the part of osmium representing, and the part of the oxygen. So the percent per hundredweight for osmium is 2.16 divided by 2.89 times 100%. And the percent of oxy is equal to 0.73 over 2.89 times 100. Okay, this is your counts on these. When you do these calculations, be sure you check, make sure your sum equals 100. You can always drop a number here and there. It's not hard to do. And you certainly want to make sure they're right. Well, this is just a quick check to make sure you have the right percentages. And once this is obtained, then you want to go through the sequence: percent to grams to moles, set up a ratio of the, I'll show you that in a minute, reduce your ratio. I'll go ahead and write reduce ratio, and this will give you your empirical ratio, and then you can write your empirical formula from that. Okay, let's move this up a little bit.
Okay, so we'll take the percentage, 74, wait, I usually start by writing out the element symbology, say osmium, and then I'll put oxygen here, colon. It's just, to me, the way I want to do it. You pick another way, but this works for me. So the percent of osmium per hundredweight was 74.74% per hundredweight, and oxygen 25.26% per hundredweight, and it adds up to 100%. Now, the next thing I have to do is, and we've done that, so I have to do grams. How do I get grams? Well, it's very simple. Drop the percent and put a G on it. Now, I'll explain the logic here in a second. Grams. 25.26 grams. If you had 100 grams of this osmium oxide, how many grams of osmium would you have? You'd have 74.74 grams. If you had 100 grams of this osmium oxide, how many grams of oxygen would you have? You'd have 25.26 grams. That's the logic that goes percent to grams. That's why it's absolutely critical you convert to parts per hundredweight. Now, what do I have to do? Go to moles. Well, I have to divide each one of these by the formula weights of osmium, for the osmium, and 16 into the oxygen. Now, what I typically do is I just put a slash right there because I know I'm going to have to divide by the formula weight, and it's 190.2 grams per mole. And just keep it separated. And then I'm just going to go 16 grams per mole, keep it simple, right there. Okay? So 74.74 divided by 190.2 equals 39. I'm just going to go 30. If you work it out, you'll see what I'm talking about. Just leave that one significant on the end down there. I always carried out 4 digits, and I'll show you why in a second. 25.26 divided by 16 gives us 1.5788. Like that. Okay, everybody still with me on this one? Got 2 elements in the formula for like this. I'll write those out. Osmium, oxide. Like that. This would imply that I'm going to have that. I'm going to put my moles up here, and then I'm going to reduce it with the common denominator. So my moles and lowest mole value. You divide by the lowest mole value in this process. So we have, for osmium, we have 0.3930, and for oxygen, 1.5788. So the lowest mole value is 0.3930, 0.3930, 0.3930, and this of course will give you the empirical ratio is going to be 1, so the ratio, it really depends on calculating this last one. And it comes out 4.017, blah, 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 it's 1 to 4. Okay? And so this will give you the empirical formula, which is simply OSO4 in that particular problem. Can everybody see that down there? Okay? Any problems with that? Nothing more, nothing less. Your biggest challenge is going to be sitting down and learning this sequence and being able to deal with it, because the problems will come to you just like. The next one is hydroquinone used as a photographic developer. is 65.4% carbon, 5.5 hydrogen, and 29.1 oxygen. These are percent per hundredweights. So as you start, you don't have to go into the calculate the percent per hundredweight based on the. Okay, so we're going to use that ratio right now, that sequence, and determine this. So how many grams have I got, guys?
65.4.
That's right. So see how easy this is? 65.4 grams and 5.5 grams and 29.1 grams. How do I get grams to moles? Say divide by formula weight.
Divide by formula.
There you go. So divide by formula weight is 12, 1, and 16. Okay? Okay, so now you've got these are your moles. I'll put a heading up here. Moles of each one of the substances. Now, what we want to do is come down here and set up a ratio, which we can reduce to the empirical ratio. And so we'll go carbon, hydrogen, and oxygen. So this would give you 1, 2, 3 lines this time. Okay? Putting your moles in, I'm going to round this one to 5.5 and 5.5 and 1.82 if you want to do that. Dividing by the smallest. Okay. Now sometimes you will get and only get a fraction. You may get it in this one. 2.25 or something 1.25 or 1.5 or 1.75. If you get that, you have the right to multiply to scale it up to whole numbers. Now, if that happens, I'll show you, but I'll show you again in a minute. So I'll take 5.5 divided by 1.8 equals, well, these are even. So that's a 3, and that's a 3, and let's see what, and that's a 1 in here. So the empirical formula for this is C3H3O right here. It out and got a ratio like this. 1.5, 2, and 1. Came out like that. What do? If it's, and you won't get any more ratios, the ratios will not come out like 1.38. They'll either come out something 0.25, chalkboard's giving up on me, something 0.50 or something 0.75, 1.25, 1.75 or whatever. If you get that, you can scale this up, in this case, multiply by 2. Whatever this number is, you can multiply by 2. The 0.75 by 4, and I think this one's by 4 also, 424. So that you wind up with a 3, 4, 2. Now, I don't know if that's a real molecule or not. I just, for instructive purposes, is showing you that. But some of the problems in the text, when you do your reductions, will have a 0.25 or 0.5 or 0.75. You have the privilege or right to scale those up to match the definition of empirical formula. Smallest whole number ratio, that is it. Came out like this. If you've got a number in here, now I'm not talking about all of them showing up in fractions, but these are unique, and one of them might come out here, one of them here, and here. And you multiply that, you get even numbers. See what I'm saying? Okay, everybody good on this? You sure? If you're confused, let me know. But this is a unique combination here. I'm just saying that sometimes they will pop up in that ratio. in this. So we're going to look at this last problem down here, and again, and the problem that you get will have to have a molecular weight, because the relationship between empirical and molecular weight is the whole number multiple. And that's very important that you consider that. Like the empirical weight times n, being the whole number multiple, is equal to the molecular weight. And the molecular weight has to be given in the context of the problem. Okay, so in this one, we're looking at oxalic acid as a toxic substance used in laundry to remove rust and stains. Its composition is carbon, hydrogen, and oxygen. Carbon is 26.7. Hydrogen is 2.2 weight percent, and oxygen is 71.1%. Of course, we immediately drop the percentage and write in the grams. And divide to convert to moles. 12, 1, and 16. Well, of course, this one's going to be 2.2. And see what we have here. Aha! This one rounds out to 2.25. This is one I was telling you about. I guess 2.225, 25 is fine. You won't get them any closer. And that's say 4.45. Let's see, 4.5, like that. So if it's close in there, you just scale it up. If I use the 16-digit atomic weight all period I tried, it'd probably be perfect. So. Okay, so our ratio, this would be the carbon to hydrogen to oxygen, and so we get 1, 2, and 3, and let's see, we got 2.25, 2.2, 4.5, 2.2, 2.2, and 2.2. So our empirical ratio would be out of that. This one would probably, let me do that one again, 26.7 divided by 12, 2.225, okay. Thought that was 2.225 right there. Well, we can make this, fudge that a little bit if you wanted to, because 5 would take 3 and then you drop it off. So you'd have a 1 to 1 to whatever that one comes out, say 4.5. About 2.2 equals 2 right there. So your empirical ratio, empirical formula is equal to CHO2. Now the empirical formula weight is, of course, a carbon plus hydrogen plus 2 oxygens. This is 12 plus 1 plus 2 times 16. And you can take atomic mass units if you want in this case. And so that's 32, 42 for 3, 4, 5, 32, 42 for 3, 44, 45, okay. 45 atomic mass units in the empirical formula. Well, you can see up here the empirical weight times whole number multiple gives you the molecular weight. Our objective here is to determine N. So the empirical weight's 45 times N, which is equal to 90 atomic mass units. And from here, N is equal to 90 over 45. I carry these things out. I know you know what 45 into 90 is, but for academic reasons, I'm assuming there's somebody out there that needs that. 2. So the empirical formula is based on this one right here, and here's your empirical formula. So I'll bring it down. Molecular formula now is distributing this 2 through the empirical formula. This is not a real symbology. You wouldn't use this, but for academic reasons, I'm putting it in CHO2 like that to give you an idea. This is distributed through, and the formula would be represented C2H2O4 would be the molecular formula in the end of this. So it's just showing you this would be distributed through the rest of the formula. So, stoichiometry of chemical equations. Okay, as indicated, what can you calculate from a chemical equation? Very, very important idea. Well, straight away, we can get moles, okay? What I call equation mass, particle numbers, as they apply as multiples or fractions of Avogadro's number, gas volumes, energy values, and solution values. Solution concentrations, let me do it that way. So the first 3 will be presented right now, and as we go through chapters 6, well, let's see, 4, 5, and 6, we'll pick up the other ones. We'll show you a brief introduction to solution data and how to deal with that. It's called volumetric titrations, and we'll do some of that in the lab also. 3H, let me move this over a little bit. Let's see, 3H2 as a gas plus N2 as a gas goes to 2NH3 as a gas. So the form, of course, is a standard molecular equation, and it's written in the lowest whole number ratio of coefficients. And one of the things you're going to have to learn in this issue is how to read an equation. Now, in this form, it is in, like I say, a standard form. I'll write that down. Which means the equation has the lowest whole number ratio of coefficients that you can write in there. Not fractions, but the whole numbers. But an equation can be scaled up, or it can be scaled down by multiples or fractions of the coefficients. I can double this equation. They're all gases, so please go with me on this. And that would give me 6 hydrogens, 2 nitrogens, and 4 H3s. It's not the standard form, but it's still a legal ratio. And how they react. 6 moles or 6 parts hydrogen will always react with 2 parts nitrogen and produce 4 parts hydrogen, ammonia. Or I could divide this by 2, and I would have 3H2 plus N2, 2NH3 would go to, and you can use fractions. 3 has H2 plus half mole of N2 goes to NH3. We're going to put it on there like that. So reading the equation says that the elements in that equation react in very, very specific ratios. And what did I just say? They react in very specific ratios. And the standard equation up there is always 3 parts to 1 part to yield 2 parts. And so if I take 3 parts of hydrogen and an excess, say, of nitrogen, I'm still going to get 2 parts ammonium. This 3 parts hydrogen and an excess ammonia will still produce NH3. But there's something subtle I didn't say. 3 parts hydrogen will only take out of this excess 1 part of ammonia. I don't care if you have a truckload of it. It's only going to pull 1. So that's going to decrease this concentrate, this amount, just by 1 mole or 1 part. So this is what I'm talking about when I say specific ratios in a reaction. You say 3 to 1, no matter how much you have here, you're only going to take out 1. The rest of it just goes off, didn't do anything. It's excess, unreacted. Because once you form the ammonia, there's nothing else to react with. Very important concept in reading a chemical equation. If you get that now, then the rest of them you begin to start developing your point of view in manipulating equations. Okay, let's go back. Now, again, what can we calculate? Let's call that an item. And the first thing I mentioned was moles. And that's when you balance the equation, moles is the visible issue that is available from a chemical equation. Where is it? Well, it's right here. The coefficient in here defines the number of moles. So in the equation, in the standard form, we have 3 moles of hydrogen gas. I have 1 mole of nitrogen gas and 2 moles of ammonia gas. Right there. Now, that's the easy part from the standard equation. Now you want to get the mass values, okay? Equation mass. Now this is not formula weights, it's multiples of formula weights. In this case, it's 3 formula weights of hydrogen. Here is 1 formula weight of nitrogen, molecular nitrogen, into a molecular hydrogen, and 2 formula weights of ammonia gas. So that would be 3 times 1 grams. Here would be 1 times 28 grams. Here would be 2 times 17 grams. Like that. So we have the equation mass for the reaction in the ammonia production is 3 grams of hydrogen, not nitrogen, hydrogen gas. And here we have 28 grams of ammonia, molecular ammonia, reacting to produce a total of 34 grams of ammonia gas. Like that. Particle numbers, and this is probably the least used of any of the calculations we'll deal with. I will have one on the on the exam that will use particle numbers. How many particles are involved in hydrogen or something like that from the equation. Well, this is the mole number in little n moles times Avogadro's number, capital N, make that a little neater, Avogadro's number. So what you would have, and Avogadro's number, as you know, is 6.02 times 10 to the 23rd parts out of the, representing the quantity of 1 mole, equals 1 mole of particles. Okay? So if I have a coefficient of 3, so I have 3 Avogadro's numbers of hydrogen, I have 1 Avogadro's number of nitrogen, and I have 2 Avogadro's numbers of ammonia, like that. So you plug in 602 times 10 to the 23rd, and you find out how many particles you have in real space, and so forth. Now, the calculations of gas volumes and calculations of energy numbers and solution concentrations we'll leave to next chapters. We'll do it. This is enough, but we'll be using this for right now. Okay. What we're given and what do we know about the chemical equation? Well, we know that 3 moles of hydrogen will produce 2 moles of ammonia. Okay? Well, I'm given 10 moles of hydrogen. The question is, how much ammonia? So I can come down here and say 3 moles of hydrogen will give me 2 moles ammonia very quickly, just like that. And then under that, I can say 10 moles hydrogen will give me what? So I've set up a little relationship here that can be transferred or translated into a ratio. So all you have to do is simply put a line between these two and an equal sign and turn that into an x, and you have a simple ratio. You can cross multiply and solve for the unknown. So here, if this is true, then we have 3 mole H2 gas times x, let me do it this way, like that, is equal to 2 moles of ammonia times 10 moles of hydrogen. So it's cross multiply, simple enough. Then divide both sides by 3 moles of hydrogen, and you'll have your answer. Now, x has no units as yet, and you know what is going to come out, but you'll find that will cause a problem in the distant future if you don't just read x as an x. It will evolve. The numbers and the quantities as well as the units will present themselves out of the solution of the problem. So x is x, it's unknown. So we have 2 mole NH3 times 10 mole H2 divided by 3 mole, that's not 13, that's 3, right? 3 mole H2. There. So the units cancel very neatly, and we're left with moles of ammonia, which is, of course, the objective of this problem. And so we have, and I'm stretching it out for academic reasons, like this. So you see how the ratio simply solves itself in context of the problem. 2/3 of 10. Say a problem that you wanted to do in the lab, you probably round that to 7 because of one significant figure in there. Okay? That. Now, we turn it on. Okay, and it says we're in an excess of oxygen. And the question is, how much of this in grams are we going to produce from that combustion? And that's not even in the problem. So I will set it up generally like that. Okay, first thing I got to do is take this 28.7 grams and convert it to moles. So 28.7 over 16 grams per mole is equal to 1.79 moles. How do you calculate moles from weight? Divide by the formula weight. So that's what I did. All right. Over here, we'll work it in moles first. So I've got 1 mole will produce 1 mole. 1-to-1 ratio. So I could set up 1 to this and 1 to X if I wanted to, but if they're the same coefficients, that means this 1.79 mole of CO2 is going to be produced in that excess of O2. Now, how do I calculate the mass? Now I've got moles of the objective, I need the mass. Well, we multiply by formula weight of the CO2. 16, 26, 28. So this is 28 grams per mole, 16, 26, 27, 28. 28 grams per mole. So grams of CO2 now, 1.79 mole times 28 grams per mole.
Stop.
Am I not done? 1.79 times 28 equals 1, 2, CO2. Corrected. Okay. So 78.76 grams. So let me show you something here. All right. Visualizing this, let me bring it up to the equation here. Let's rewrite it in CH4 grams plus 2 O2 grams goes to 1 to CO2 grams plus 2 H2O liquid. Okay, now the problem gave us 28.7 grams of this and asked us to calculate the grams of that. Now, in the context of what's here, it's really not very visible as far as the answer. But if I come down here and say this is 1.79 moles, you immediately say, well, the coefficients are the same, so the moles are the same. So in getting to moles, you can look at the equation. And what if it had, hypothetically, what if this was a 2 there? Well, that would just simply be a 2. You just scale it up by 2. What if it had been half of there? You divide it by half. And at the end of this, they want grams multiplied by the formula weight of whatever the target substance is. Well, of course, that's not going to be a 2 there. And we'll see some that will be exact. Okay. This is problem 379, having 10th and page 121. Okay, it's in the 9th edition. Butane burns in oxygen to give carbon dioxide and water. What's the amount in moles of carbon? Just did that. Carbon dioxide produced from 0.41 mole of something like this. Okay, here's the question. I got.
Just butane instead of methane this time?
Hang on, we'll get it. C4H10. And butane is a gas. And we have 13 O2s. And that's going to go to 8 CO2s and 10 water. And they're talking water gas in this problem, vapor. There's the different forms. And they gave us what's the amount of carbon dioxide, just what we produced from 0.41 mole of the, and this will be an excess. Like that. See the answer already? How to set it up? The ratio is right there in front of you. 2 to 4.41 is 8x. There it is. Everybody good? No? Want me to say it again? You don't see that. Usually y'all go, I got it. But y'all didn't do anything then.
Yeah, can you redo it?
Yeah, thank you. Just kidding, guys. I'm just trying to get y'all into it. You see what I'm saying? Okay. It's really you're setting up the answer as you write out the problem in this. I don't even put anything in. That didn't take but a second. Just what Scott was mentioning in terms of why I put an excess in there. This establishes more of one reagent than the other to be sure one of the reagents completely reacts out that you're interested in. But the limiting reagent is that reagent that completely reacts out. And what does that mean? That means the reaction stops. It means it's a limiting reactant. Some people will refer to that as limiting reagents, like that. If I had H2 gas plus O2 gas goes to 2H2O as a liquid, this says I have 2 moles, got to have it. Got to have 1 mole here, and I've got to have 2 moles here. Okay? What if we had 5 moles instead of 1 mole? Would I use up all 5 moles? No. How much would I use up with this data? Just 1. What would that do? So I will use up 1 mole, and so that'd be 4 moles O2 remaining. Good? How much hydrogen is left?
0.
Where's my roll sheet? I'm tired of talking to myself. Scott, you brought it up. How many moles of hydrogen is left after this reaction?
None.
Ashton, you agree with him?
I said none.
How many?
None.
None.
I said none like 6 times.
This in an excess gives that. Yes, sir.
We've all been saying the answers.
Okay. Thank you. That helps. Gives me some encouragement that I'm not dead yet. Anyway, 5, you used 1, and you got 4 moles left over. Hey, let me finish this. It's real important. And you've got nothing left right here. The nothing left is your limiting reagent. because the reaction stops. And the reason you have this leftover is the essential excess. Yes, sir.
I was just going to ask you that.
Okay. What's the limiting reagent? So this is your limiting reagent, reactant, and this is, of course, the excess. Well, determining from a complex problem what is the limiting reagent is not as complicated as some people think in terms of working. This is called a rebreather equation, for what it's worth. Notice on the end it's got oxygen, and this jewel on this left end is called potassium superoxide. In the presence of water, it generates potassium hydroxide and oxygen. And there have been extensive research and development in rebreather devices, underwater devices using this, so that's not the point. Okay, the given is 0.25 mole of potassium superoxide and 0.15 mole of water fed into the reaction. Which one's the limiting reagent? Meaning that the one that goes away first, okay, will stop the reaction. The other one will be an excess by the amount used relative to the moles and coefficients and what have you. Okay, now I'm going to give you my method here. Once you're in moles, right here, divide by the coefficient. So if I'm working with the potassium superoxide here, 0.25 over 4, is 0.0625. And if I'm working with the water over here, I have 0.15 divided by 2, and that's 0.075. Since this number is the smaller of the two, this is your limiting reactant, superoxide. Now, caution. This is only a mechanism for defining which one of the reagents is your limiting reagent. But when you solve the problem, you do not use these numbers. Are we clear on that? Don't use this. You go back up here and use those to define your problem issue. So we go back up here and we look at the ratio 4 to 0.25 and 3 is to x. Not excess, x. Okay, so let's see if I can keep it off on the board here. So that's 4 is to 0.25 here on the, and 3 to x. So that gives me 4x equals 3 times 0.25. And so that is x equals 3 times 0.5 over 4. Let's see. Wait a minute. 4, yeah, over 4, and 3/4 of that is what? .188, and then of course times formula way if you need grams of that. Everybody good? You know? Now that's a very simple, straightforward. It doesn't matter how complex the problem is. If you'll divide moles by the coefficient, and the smaller number is your limiting reagent. But keep in mind, you go back to the given data and work the problem ratio through that. Okay? Now, if this is the number of moles of this produced, okay, you use this much, how much of this stuff remains? How much of the water remains after this? How much are you going to use in this? Okay, 2, 5, 4 to 2, 5, 2 is to x. Look, take this part right here. How much of this water is going to be used in this thing? Make this an x and work your ratio, just like that. So I'm going to come over here. 4 is to 0.25 equals 2 is to x, and so 4x equals 2 times 0.25, x equals 2 times 0.25 over 4, that's half of that, 0.125. So you use 0.125 used, but you have 0.15 mole. So 0.15 minus 0.125, that's 5, 1, 2, 3, 4, 5, 0.025 of the water's left over you didn't use. You have that kind of question coming up on exams too. Okay? How did I do that? What did I do? I went back and took the given, and I know this is the excess. I take the excess and make an x out of it, and set the ratio up and solve for the x. That's all it is. It tells you how much is used. Well, if you got 0.15, you only use 1.125. You got that much left over, 0.25. Cross multiply, and you got it. How much was used? But you didn't use it all. Yes, ma'am?
So the 0.025 is how much water was used?
0.125.
0.25.
Right here.
0.25.
Now that's what's left over. Okay, the 125 is up here. See, I took it and subtracted it right there. Okay, I'll do it again. No problem.
No, we're good.
I'll give it to you. Hang on, watch out. Watch out. Watch out. Okay, we know what we're given 0.15 mole. Okay, that's what you're given. Okay, we know this is the limiting reagent. We just did that a while ago. If this is the other one, not the limiting reagent, make it an x. See what I just did? And so it's 4 over 0.25, 2 to x, solve for x. That's what was used. Does that make sense?
Yeah.
Guys?
Yeah.
Okay. So that was amount used. So we'll 2 times 0.25 equals 4x. That gives x to equal 0.125 mole used. Yes? Okay. Now, we're given 0.150 mole in problem, but you only used 0.125 mole. Left over, if you're living in the South, it's 0.025 mole H2O not used. That makes a little better sense? You good? Okay. Those are formula weights. Up there. Got those down. Now, I recommend, in working complex problems, or if you get something like that, write the formula weights over the formulas, whether you need them or not. It's just a habit I've gotten into. More times than not, you're going to need the formula weight for something. Okay? And so you're given a vessel that contains 4.15 grams of titanium oxide, 5.67 grams of carbon, and 6.78 grams of chlorine gas. Which one of those is the limiting reagent? Everybody listening?
Yeah.
Convert to moles and divide by the coefficient. The smallest number is the limiting reagent. How do you convert to moles? Divide by the formula 8. Good. And that's why I put them up there. So you just simply come up here. 80, 12, 70. And so that's 4.15 divided by 80. And so I have 0.052 mole here. And 7 divided by 12. 0.473 mole. And this is 6.78 divided by 70. And that's 0.097 mole. And so then I'm going to divide each of these by the coefficients. So who's your limiting reagent?
Chlorine.
Right. So everything has to go back up here to this mole of chlorine right here. You work the problem based on that. This just tells you it's the limiting reagent. Right there. Now the problem asks us to calculate, let me find it again. Now here it is. How many grams of titanium chloride, titanium 4 chloride, can be produced? So the question is here. And they want it in grams. First work it in moles and then multiply times the formula weight at the end of it. See? Moles is a ratio. So here is 6 to 0.097, 3 is to x, right there. 3 is to x, and 6 is to 0.097. Got it? 6, right there, it's given. You calculated by divided by formula weight, 0.097 is equal to 3 over x. So 6x equals 3 times 0.097 moles, which gives x to equal 6 and 0.097 mole. 0.097 divided by 2. And so we have 0.0485 mole of the titanium chloride. How many grams? How do I get it? Thank you. Got somebody listening. Times formula weight, which was, I think that says 220, times, I'll just come over 0.0485 times 220 equals 10.67. See what I've got here. Still need to do theoretical and percent yields. We'll start with theoretical and percent yields next time and finish this in the beginning of the next class.